So we're going to put that guy here. So the way this H-bridge works is you see those two giant green connectors. Those are where we connect the motors. And so we also have this blue connector. This is where the power from the battery comes in that goes to the motors. So obviously power comes in here. If the motors are turned on, it goes straight through to the motors. But when you want to control the speed, or you want them to go forward or reverse, use these control pins to change the direction. And then in my experience in the past, and yeah, same thing here, we have ENA and ENB. So this either turns the switches on and off for the motors. So you can have them on, full speed ahead, off, going nowhere, or you can pulse them using pulse width modulation to control the speed. So ENA and ENB control the speed, in1 and in2 control forward and reverse on one side, in3 and in4 forward and reverse on the other side. Okay. Motor driver mounted. One more silver bag. By the way, do you know why these bags are silver? These are called anti-static bags. Electronic components here can be damaged by static electricity. You see this integrated circuit here. If you know, when you walk across the carpet and you touch the doorknob and you get a shock, that's a lot of static electricity built up kind of on your body from just the air, and the low humidity causes that static electricity to build up. And so if you touch that chip, you don't even have to see or feel a spark. Those sparks are somewhere in the thousands of volts, but only 300 volts can damage a chip. Now, some people say once the chips are mounted on the circuit boards, then they're protected, and some people say they're not. In fact, in professional labs, even anytime you're handling anything that has electronics connection, even if it's a solid box of metal with connectors, you can damage parts inside through those connector pins. So they will use full protection all the time. But the chip manufacturers have gotten pretty good. I mean, when you look at a hobby device like this, how much is reliability a requirement? Probably not super high. Functionality, performance, those types of things are more important than reliability. But when you look at an airplane in the sky or a satellite in space, reliability is one of the highest priorities. And so that's why they do that in the professional labs. Anyway, enough of that. So this, what do we got here? 16 channel, 12-bit PWM driver. So this is our pulse width modulation hardware, and this is what's going to control the speed of the motors. Like I mentioned, it's going to go to ENA and ENB, and then the pulse width modulation will control the speed. The Raspberry Pi, it can do PWM, it can do basically what you might call software pulse width modulation. And it takes a lot of resources inside the Pi to do that. There are some libraries that do that. Oops, I can't see over there. There are some libraries, Python libraries, that you can get to do that. But as Pi's rev, they come out different revisions and stuff. Sometimes the libraries aren't updated and you have problems. So it looks like what they've done here is given you basically a digitally controlled PWM system in hardware that does a couple things for you. It offloads the resources from the Pi, and it gives you very, very good control over the speed, hardware control over the speed instead of software. The thing with a computer like the Pi running an operating system is you can be trying to pulse width your motor and get an interrupt from the Ethernet chip, and that has a slight disruption on the PWM control if it's being run in software, so that won't happen here. Okay, hardware is now mounted. Let's wire it up.